Okay, welcome back. I hope everybody had an enjoyable spring break. This is week 9. We will discuss regression and also how to conquer the problem of overfitting using regularization. We have quite a lot of stuff in the outline here. Because at the last 30 or 40 minutes, I want to give you another introduction of this highly variable gene study. Okay, so this study uses a feature of variability among cells to look at their gene expression variance across individual cells. And it tells you a lot of cell function rather than the average expression of the genes. So this gives you some concept shift if you only focus on the compare gene expression levels, but not the variability. But before that, we will introduce certainly regression method as a group of methods, okay? And then we will discuss linear regression models, single variable, multivariables. We will look at how to compute those coefficients to fit the linear regression model. Basically, you use optimization to estimate the best coefficient combinations. Depends on your dimensionality of your problems. You have to estimate the values for all the beta to establish your linear regression model. Then I will introduce lasso, LA, SSO. This is a very important regularization technique, and also people use this widely to do feature selection to see which variable is the most important to contribute to explain the response variables variability. So in the discussion with the data scientist or statistician, they will use lasso. They won't tell you exactly what lasso means. They just use this term because it's such an important technique, and you need to have a basic understanding in order to have a meaningful conversation with a statistician. When they say, I will use lasso to feature select your variables, you know, after this lecture, you know what that means. That will be okay for you. You don't have to know quite a lot of details because we will use some computational exercise session to study some numerical examples to let you to understand that better in Thursday. So I don't know you have some impression of what linear regression is. If you have an Excel spreadsheet, there are protocols. If you have 2 columns of variables values, this, and then you can follow this procedure to see, okay, I want to build a regression model to use those variables, 1 column, 2 columns to explain the 3rd column, something like that. If you plot them out, if this is like 1 variable explained to another, so you have independent variables, okay, your x-axis and dependent variable on your y-axis. So you have something like this. If you use some R package, you can generate a table by fitting the model, and you have an estimation of different variables and also those coefficient numbers. So that's your general impression of the linear regression model. Well, this part is in R in MATLAB, I believe. They all generated this same kind of estimated coefficients. So this lecture will help you understand what those means, and then how those are computed in theory and also in computer, the background algorithm. So the application will, in our single cell data, will be you use the combinations of gene expression to predict some features or some characteristics of quantitative trait of the cells. Okay, if you can assign each cell a value, so something like pseudo time or T cell exhaustion and the cell size, whatever. So whatever you want to predict those cells feature, and using other combinations of the gene expression. So this is a scenario we can apply linear regression to see which gene is the most important to associate with the feature you want studied you want to research for the cells. So in general, regression model, this method is supervised learning method. You need to have your sample. You have to do experiment or test to get enough data points. You have enough X and Y to use X to predict Y. Once you establish the model, so you can predict if I have another X in future, what my Y should be. Okay. So if you don't train the model, you have no parameters. You have no estimation of your model parameters. So you don't have any power of this research. So globally, you have your independent variable X. That's a pair. So you have X, you have Y. Just imagine you have two columns of information of all the numbers. You want to establish a function to transform every individual X into the Y value to make them match to each other. So you do this mapping, okay? You don't know the distribution model. You just estimate, you establish this relationship by introducing this function, okay, F. So X is a vector, it's a feature vector. Depends on how many features you want to use. So you have P dimension, okay? So in this formula, I consider X, Y as vectors. So the Y is something you want to predict for. So this vector here. And your X is here. Okay? I don't think I'm correct. Yeah, so X, this is a number. So I write in this way. So this is just single number. You use this P dimensional descriptive variables to predict Y. Okay. When I see if you have a multiple Y, what I mean is you have let me write in different ways. So now this is Y, okay, a single number. You want to predict it using X. X is P dimension, so P values. To predict the Y value. This can be, in my next example, will be the price of the car, and then you have what type of car, how many, the engine size, whatever, all the features to predict the price. The way I write that into a vector of Y, make this long, is because I have a different type of the cars. And here is a matrix. The training data still has to be paired. So you have one type of car, you have all the features. another type of car or the features. Okay. So that's why I'm writing y in the vector, because you have n samples basically. That's why y is a vector. So this mathematical formula is you build this relationship to convert x into y. So this function. So if you apply this function to x, this become an estimation of y. Okay, so this is like estimation of y. The problem of a regression problem is you want to use x to predict y and make this compare to each other. And this is the difference, basically. Okay? And you want to make this difference called loss function. This loss, the difference between these two, the prediction loss, the estimation of this loss function as small as possible. So you can select different combinations of this f parameter to change the mapping strategy or power, whatever, and to make this estimate y and the real observed y as small as possible, the difference between them. So that's what I mean. So this loss function has a feature, and this should be, if you have a same values to compare, the loss function will be 0 in the value, because that's a perfect match. So convert that into a least squared problem is the difference between the estimated y and the observed y, and then the L2 norm. Basically, that's squared every element. Summation should be small as possible. To solve that problem, we need two key concepts. In linear algebra, we will rewrite this in the vector or matrix multiplication format. So we need the understanding of the inner product. That's two vectors production, and then become single number. So to do this, you know how to do this. Okay. Another is a norm of vector. So the norm is how long this vector is. Okay. So to use dot product, I will write two vectors. The first is this beta. Okay. So this, then you have x. So this represents a condition which you have only p equals 1. So in something like this, if you only have one variable, then you only have this to predict y. Then the beta will be the coefficient for the linear regression model. You have beta 0, beta 1. And here you put 1 in the first element of x. Okay, you add one extra column here, but put 1 in here. So this feature variable space becomes p plus 1. So in this case, the p equals 2. So you need 2 elements to do this. So when you do the dot product between beta and x, okay, you get this expression. All right. So this expression, this is a constant. Okay, if you fixed their y, so this will be c. It's a constant. and the beta 1 becomes beta 1. This is slope of your regression line. So that's x is your variable, and then this is your predicted y. Okay, so that's why this linear form of the definition of this line can be rewrite into the dot product. In this example, you have feature variable space dimension is 2, okay? So you use 2 columns of the features to explain your y. And you can have more. Same idea. If you have 2 feature variables, you put 1 here again, and that's your linear model coefficient you want to estimate beta 0, beta 1, beta 2, because the dot product of these 2 variables become expression like this. So this is if you use this to approximate y, and then you can write that into y equals this. This is like a 2D regression, okay, 2 variables. So for most of the case, we will just use this as an example to explain the concept. But you can expand this to multi-variables. You have a beta 1, beta 2, beta 3, many features. Remember, when I say features, I'm moving towards that direction. I'm not talking about how many samples. You can use hundreds of samples, or you can use a couple of samples, depends on how deep how high this table is. But I'm talking about here, beta 1, beta 2, I'm talking about this feature space, how many variables you want to build into your model to explain. I'm not talking about how many samples, how many data points you have to estimate those values more accurate. You have more data, you probably can make this estimation more accurate, but that's irrelevant to how many feature variables you want to use. Feature variables, how wide this table is, defines how many beta 1, beta 2 you will use. I will have concrete examples to show you. I will leave this norm to later when we have regularization problems. Basically, we have 2 types of norm. One is called L1 norm, and another is L2 norm. If I don't tell you anything, normally I mean L2 norm. This is the length of the vector, and you know the formula here. L1 norm is even simpler, and that's only the absolute value of each element in the vector. Okay, if you have for example, beta 1, beta 2, beta n, okay, so beta p, okay, how many variables, you can estimate the L1 norm of those beta, just calculate the sum of the absolute value of those beta. Okay, as I expressed, I said, if you only have 1 variable, it's called simple linear regression. You only use 1-dimensional feature variable x1, okay, x, to explain y. So single predictor for the y. If you use more than 1, this is called multiple linear regression. In that case, you have x1, x2 to x, this should be xp, okay, to differentiate it from the difference from number of samples. This is not the number of samples. This is how many feature variables you want to use to predict your y. Example, okay. Simple regression model. You want to predict the price of this vehicle, and then you use a single variable x, which engine size. You can build this model. The price will be positively related with engine size. Okay, so this term is beta 0. Okay, just give you a slope in this curve. What that means is the unit difference, engine size, use some other unit, which price, if you use dollar or as the price. So this is if you don't normalize or centralize the price, then you use this term to do this slope. Not the slope, the intercept. Okay, is that clear? If you use multiple, okay, more than one p, okay, you have multiple feature space, variable space. To predict the price, you use not only the engine size, but also horsepower, peak, RPM, lengthwise head. So you use 6 feature variables in this case, and it's P6, okay? To build this model. So by looking at this picture on the screen, you don't know how many samples in your model fitting. This only gave you the idea how many feature variables you use to build into that regression model. You can certainly use more samples to make your prediction. So the prediction is those values, estimate values. Okay, some positive, some negative. This length, okay, looks like a negative, correlated with the price, total price. Engine size, the larger, the more expensive. Horsepower, the more powerful, the more expensive. So those can tell you the relationship direction. Another important is at the end, how much the variability you explained in your sample. Okay, if you have a perfect fit, then this will be close to 1, this value here. But in this particular model, there are 81% of this variability has been explained. So again, from this screen example, we don't know how many samples they use. We don't have original data. What you have to understand is N and the P are different. Okay, we're not talking about how many N's here. It's not 6N, it's 6P, 6 variables. Okay, to write this framework into matrix format, this is very similar to what I'm doing here. So Y is N by 1 vector. So if you consider the car example, this will be different brands of cars, okay? Different samples they obtained the information from. And then you have P plus 1 variable because you add 1 constant column of 1 to estimate the beta 0. So in the previous example, you have a p equals 6, equal to 6, okay? So you have y, and then x become a matrix because x contains information of n different samples. Each sample have a p variables, the whole matrices, and also extra column of this 1. So that's n times p plus 1. That's a dimension of x. So you want to build a model to transform this x and into give the predicted y, okay? So y prediction. So that's a linear regression model. So what we need is a vector of beta. The dimension of this is p plus 1 times 1, okay? So this is a vector. So for each feature variable, we want to assign a value, beta 0, beta 1, beta 2, beta, to give the weight. Okay, beta sometimes write as a w, so weight. To give weight for each feature variables to indicate the contribution, the magnitude of contribution of each feature variables in order to explain the y at the end. Is that clear? Okay. So this is n by 1, this n by p plus 1, and we can write the multiplication form. So if you multiplicate matrix M with beta, you probably have to transpose this in order to make the multiplication meaningful, because we have to have inner dimensionality match. So it's 1 to n, n by p will be okay. So we do this. Sometimes you write the beta times x. Sometimes you write x transpose times beta. Just make sure the dimensionality is right, and in order to let you to do this multiplication between the vector and the matrix. The end product of this will be a vector of estimated y, okay? So end product of this will be y hat. This will be n times 1. It's a vector, okay? I think that's the expression of that part. Then you can use this to minus y. So you have y minus y estimate. This becomes vector of this error, okay? The sigma. So this error vector is the difference between your estimate y and the observed y. How good your model, that's a combination of these values, will be estimated by the difference between your estimation and the real observed y, two vectors. So you can change the values here by different methods of optimization. Say I want to change beta 1 from 0.5 to 0.52, and then see whether after the matrix computation multiplication, the difference between y minus y hat become smaller overall. Okay, you take a norm for this error term. Okay. So this is a multiplication of x and beta. X is a matrix, beta is a vector, and this is write out all the terms. Okay. So each row here will be one sample, and you use your model to predict y1, and that's the pair to match. And those values, beta 0, beta 1, are the same. Okay, there's only one beta 0. It's not independent. They're everything linked. So beta 1, just a single number. So if you change the value of beta 1, every row will change the value. So you want to find the best combinations of beta 0, beta 1, beta 2 in order to allow the difference between this and observed y, the whole vector, two vectors are the smallest as possible. That's called fitting this multivariable linear regression model. We want to find the best combinations of the beta vector values in order to achieve the best prediction of observed y. I think the beauty of this is you can write the whole thing. You just use this very simple matrix form or matrix multiplication form to represent the whole procedure. This example is to use two factors, two variables. Okay, p equals 2. You have x1, this column data, x2 column data, and then y is yield. It is, and then you have x1, x2, these two variables combinations, and gave you the prediction of y. So you need to build a line, a plan, basically, use these two variables to predict your y. This is a prediction, okay? This n samples, 2 p equals 2, two variables, and to predict y. So you put that formula in, and then estimation will be 3 numbers for beta, and this is beta 1, this is beta 2, this is beta 0, okay? Your final regression model will be y estimation equal to this plus this times x1 plus this beta 2 times x2. And this is a plan, okay, to give you a prediction, the combinations of value x, y, and then you predict x1, x1 to predict the y. Okay, so this is a basic framework, and here is introduction of term. You don't have to remember, well, we can mention this. So univariant, multivariant analysis. So this is not the same as what I said, the multivariable. So when we talk about the multivariant, we mean the output of the model have multiple y, okay, more than one y. We are not going to deal with any of this analysis in the whole class here, but I just want to mention when you see multivariant analysis, it's very, very different from multivariable analysis. Multivariable analysis or single variable analysis is always have one column of y. Okay? If your model will fit give you two columns of y, you have y1, y2, then your analysis becomes multivariant. Okay, this is just terminology. So when you see simple regression, basically you are talking about single variable regression model. When you see multiple regression, that's multi-variable regression, but still your output is a single y, okay, single vector. When you talk about multivariant regression, then your y become, okay, more than one columns. But we are not going to do any of those analysis. Just terminology. Okay, this is a numerical example. Let's write in a slightly different form, but it is the same as the matrix multiplication form. I just opened up to write in this way. This is an example. If you have 3 points, okay, you have x is 3, 0, -3. So in your x, there's n 3 samples, n equals 3. Then you have y corresponding response variable y is 4, 2, 0. So you have 4, 2, 0. And then your input x, the 3, n equals 3, 3 samples. So you can write, if you write every single equation out, you have 3 equations. But if you write in the matrix multiplication format, that will be this vector times this vector, okay? So you can write in this way at the end, just that. Yeah, so our problem is try to find the combinations of the beta, okay, values to predict p+1 beta values in order to minimize this whole thing, okay, to minimize this. So what is this? So y is your observed values. So this y here is this vector, observed. Your observed minus your model. This will beta 0. You give the prediction of the values, so you plug that number in here, and then you plug in every single 1 to p values and multiplicate by their observed x. So the whole thing, this will give you the prediction y, predicted y. So the difference between these two and the squared and also summation is called the whole thing. That's the term you want to minimize. You want to make this difference as small as possible by change the value of beta. So that's the expression of this. So how can we compute that? So we know we can express linear model in this way, right? Remember, beta contains beta 0, okay? And the p different values, a vector. So if you change the form and you move beta to this side of equation, and then just use, if you use y divided by x, you should get beta. Okay, that's true. But because x is a matrix, so it's not just division, not a single number. what you have to compute is the inverse of that X matrix. Then if you know how to compute the inverse of X matrix, then you multiply it by Y, you will get beta directly. So it's not very hard to compute, because you can express this in this matrix multiplication. But the problem is, what is the inverse of the X? So if you have squared matrix like A here, and its inverse and the multiplication of these two will be an identity matrix. So that's the definition of the inverse of the matrix. So it's not very simple to compute the inverse of a matrix. Okay, so the expression very simple, but the computation is very different from just divided by a single number. But the concept will be similar. So in MATLAB or the other language, you can have this, you have Y here, then you inverse the function and multiply it Y, and then you get the beta estimation. So computationally, you can achieve that if you know the inverse function of matrix. So what is the, if you don't have a perfect fit? So here are all the examples. I have numerical examples of perfect fit of these sample points on this regression line. There's no errors. Well, in real situation, you can fit a line as much as possible to achieve so-called least square errors. You try to find this definition, this line, and to make the distance from each observed point to, if you draw a line along the y-axis, to make those yellow, okay, distance as small as possible. So that's what you want to achieve by fitting the model. There's no way you can perfectly draw a line and go through all the observed points. So you want to compromise yourself and try to make a line that goes through in the middle of the majority of the points. So make the total difference between observed to the predicted value as small as possible. So this is this square, the concept. There are some mathematical formula to derive this, how to compute this least square, how to achieve this least square objective. So in this way, people write this, the residual of sum of squared, so RSS beta, give beta as a combinations of beta values for this particular given beta setup, and you compute the observed and the expected, the difference and the square and the summation. And this can be rewrite into matrix multiplication format. Okay, the transpose this difference multiplied by that, and there are some derivative of the normal equation, and to establish at the end this relationship to if you have the best combinations of values of this, you will give the corresponding y expression. So at the end, okay, so you can, for example, move this part to this end, right, by taking the inverse of this this thingy, okay, this multiplication, the x transpose times x become a square matrix. But if you move that to that side, you give the beta value. At the end, this is the same as the so-called pseudo-inverse, okay, of x. If you don't do the pseudo-inverse, if you do directly to inverse this x, it's difficult to compute. X is not a squared matrix because it's n by p. However, if you take the formula derived here, at the end you will achieve something like this. And we jump to the conclusion. Okay? So you compute a transposed x multiplied by x itself. Okay? This becomes a squared matrix. Then you take an inverse of that product, then times x transpose, then times y. That gives you the beta. The solution is the same as this. Okay, just move x to that end in order to achieve estimation of beta. But this is a more computationally stable. Okay, it's not report error or a lot of the instability in the computation because of the transformation of this operation. So to achieve that so-called normal equation to solve the linear regression problem to estimate the beta values, you have to use some knowledge of so-called matrix differentiation. So for this particular equation, the derivative of those equals 0, and for this form of the equation, the derivative of beta is this. But that you plug those terms in this estimation of errors. At the end, you will achieve this, how to estimate the beta, use this so-called normal equation. So this is a normal equation. Okay, so this is a normal equation to help you to compute the beta values. It's the same as if beta x transposed y. Okay. But computationally more stable. So that's why we do this transformation, multiplication. And they can confirm with numerical examples. So you remember we had this. If you do this operation, this kind of a transpose x times y. And the same results as the inverse of this. Okay, it's basically just copy the formula to here, and you get the same results. So those are the MATLAB examples. We will try. This is the first way you can. Then you have this formula. You can use pseudo inversion. This so different ways to compute the beta values. And some use the normal equation, some use pseudo inversion of the matrix directly. This is inside the pseudo inversion function. We actually use SVD, decomposition of the matrix. But everything at the end linked together is all the matrix multiplication, inversion multiplication, okay? This is a very beautiful in theory, but in reality, this normal equation computation is really expensive. So we don't, when you do the linear regression, the algorithm will not use this analytical solution. It will use optimization, just guess the values of the beta numerically. So we need to reformulate this into the optimization problem. So what we have to is to establish a loss function. The loss function is this, okay? So x times here change to w is beta, basically. Then minus the observed y, and then you take norm, and you try to make this as small as possible. That's fitting the model. So you change the value in beta in order to make this small. So optimization, and we had mentioned that in the previous slide. This is a procedure. You just change the parameters, and I use this as an analogy, as example. So I can change the parameter of this here, this, and that. Maybe I can change this. So I can tune this panel. And each time I change a variable, I will ask you, do you feel more beautiful this sound? You say, no, I will change another. So I can have many different ways to tune this parameter values until all the audience say, okay, good, then I stop. So when I tune these parameters, this is a procedure of optimization, but I need your feedback. Your feedback is my loss function. So I want to make the loss function or your satisfaction as big as possible, my loss function as small as possible. So that's why the procedure is like this. I change parameter of your setup and then test to ask loss function, see whether this is a good move or not. If not, I change another way. So in our least squared function estimation is the difference between expected and observed. So we try to minimize the distance, total distance. So that's a function optimization problem. If you have optimization engine only give you the minimized, then you just take negative. You just put a negative sign to the likelihood function or loss function, so you can flip this problem to achieve either maximum or minimized optimization. So that's a procedure I just described. You start from an initial guess of the parameters, okay, maybe just a random set of data, and then give you the function, likelihood function or evaluate function or objective function, whatever you call it. Then you set up some cutoff, say, okay, if the likelihood function is good enough, I stop the search of the combinations of parameter. If not, I'm going to set up a new set of parameter values and try again, okay? So the art of the optimization is in this particular step. If your objective function is not achieved very well, so how can you change the combinations of your parameters? in order to achieve that target as soon as possible. So how you reset your parameter, not randomly. Okay, if you start randomly all the time, it's still a kind of algorithm, but that will not help you to very quickly achieve the best results, which to best fit or smallest loss function or objective function achieved, whatever. So the optimization is kind of a numerical art, and to help people search large parameter combination space in order to achieve the objective function as soon as possible. Use minimized steps of computation. So once you think, okay, it's good enough solution, I gave you the solution. Solution will be the combinations of values of your parameter in your model. So over the years, we have many different ways, gradient-based, direct search, okay? In MATLAB, there are built-in functions, so you can achieve minimized function. Achieve for this function, there are boundary problems, so you have to have solutions between this and that, and you search within this region. There are more dedicated toolbox in MATLAB, the optimization problem solving this toolbox. There are functions for different scenario use. Okay. The most important concept is a gradient descent. This is a 2D. You search for x1, x2 combinations, two feature variables, and that's your objective function. Or loss functions. So you want to have a combinations of x, y, x1, x2 values to minimize this loss function. So you search for this whole space. If you use 5 here and 10 here, you will end up with a corner somewhere here. Then you look at its loss function, it's still very high. Then you try another combinations, 0, 5, then you found another place. But how can you strategically or systemically search this combination space? In this case, it's only x1, x2, this 2D space. Relatively easy, but if you have many variables, okay, this is high dimensional space, how you can search this space effectively? So the object function to achieve the smallest value of the loss function, so minimize the loss function. So the strategy was to use gradients. So you move a small step away from your previous step combinations of the parameter setting, and then see whether you move to downward of your slope across this space. If that direction is all right, you take that step, and gradually you move to the minimized position. And this strategy, you can have a parameter, say, I want to, how long the step should be, and what direction, or whether I will always take that low direction, or sometimes I will jump to the other direction to search for non-local minimization solution. So there are different combinations, different ways to do this gradient descent algorithm, but that's basically the concept. You need to have a derivatives of your cost function in order to compute the gradient. Okay. Yeah, so some examples. You start from here and search. This is like a 2D, so you have to compute 2D derivative gradients, and then you have a beta, and there's two variables, okay, beta, W. and then you take steps to achieve this lowest loss function value. Linear rate, you cannot jump too far away, and you have to take small steps. But the small steps problem is you was trapped within this suboptimal solution, local minimized position. You cannot find the global minimization. If you jump too much, you just get lost in this space. Okay. So for this linear regression fitting problem is we can easily reach to the overfitting problem. If you have a lot of P, so P is a big number, 1,000, then you have a very, very long table. Okay. You will never have enough samples to accurately estimate all the parameters here. But if you put every variable in, you can easily achieve perfect solution for Y, because there are so many combinations you can take to give that perfect fit. To illustrate that overfitting is if you fit your model with this, you probably still have quite a lot of errors. Okay, but this is just one feature variable, okay, beta 1, theta 1. But if you introduce more terms, this probably is okay, but if you have many, this model will explain your observed variables very accurately because you introduce so many parameters. But you overfit your model. But next time you have a prediction, you have new data points come in, you will not be able to predict that you use this overfitted model. So we want to achieve some balance between how many parameters we want to use to select, to build in this model, and not overfit it. Okay, we want to achieve some balance of that. In this term, if you have 1,000 variables, you probably want to select, okay, this is important. I will have this beta 3. I will pick this beta, maybe 14. I will pick this beta, 250. So I probably just use 3 to fit my model instead of use all the variables. So we want to solve the problem of overfitting. We don't want to use all the parameters, feature variables to explain our samples. We only want to pick the most important ones. Okay. So how can we achieve that? That's the procedure of the regularization. We want to regularize those parameter space rather than use full spectrum, all the variables. We just pick those most important ones. So this procedure will be to solve the overfitting problem. Okay, 5 minutes break. Okay, come back at 10 past 11. Okay, the overfitting problem is not only limited in the regression, it's also in the classification problems. So you want to find a right separation and using the right numbers of the feature variables to explain rather than overfit every single individual observed values. So how can we do that? It's not too hard. You can select those values which contribute the most. If you look at the beta values and see if you have a cutoff, say beta values smaller than 0.5, I will set those contribution to 0. Okay, in this particular example, you have many feature variables. So you have estimation of all the beta, there each variable's contribution to the fitting. And then if you see, okay, do regularization, set a cutoff. If this contribution is too small, 0.03, I will reset that into 0. In that case, you actually just eliminate that particular variable, feature variable. You only select those top ones. That's it, okay? So this is a regularization, okay? There's a problem. So when you fit the data, you don't know which one is important, so you fit everything in there. There's some kind of a logical circle. So you want to select the most important ones to fit your data, but you didn't know you use everything, then you drop out and use the most important and do that again. So there's a better way introduced by Robert Tapashirani in 1990s. And their solution is to add another term in this regression loss function. What they add is this norm term. So this norm term is the L1 norm, is basically those values, absolute values of beta summation. Okay, so this is the difference between observed values and the regression fitting model. Okay, observed and expected value observed, that's difference. And then they add this loss function, another term, is the total absolute value summation of the beta value. Basically, they let the program to fit all this, and then they just summation of the beta 1 plus beta 2 plus beta 3 beta k. So I that term as a penalty to this loss function. So you can have a lot of beta values, no matter how big, how small the beta value, you can sum them together in order to achieve the best prediction. But because that gave you the penalty more when you introduce more beta. So you have to balance between how many beta non-zero values you will include in the model, balanced against how better you predict your points. So every time you give, say I will select beta 4 included in my algorithm, also beta 4 gave some values built into here. So introduce a beta 4 give you a better prediction, so make the observed and predicted value smaller, but you make this term bigger, so make your loss function even worse. So you have to balance whether you want to include beta 4 into your model or not. So once you introduce this term in the loss function, the algorithm will automatically take care of those balance. And also you give this so-called hyperparameter lambda, and to see the contribution of your variable introduction. So you want to introduce less variables into the model, then you set a bigger lambda here. Okay, so once you introduce some non-zeros, this will be maximized or amplified, give you the worst loss function. So once you have that term, so basically this is lasso, okay? The name is called least absolute shrinkage and selection operator. Basically that's the innovation. So lasso use L1 norm, so that's here, okay? It's a term. This is still the regression term. Okay, if you look at the value here, it's just the parameter. We use beta in previous examples, but here they use theta, the same thing. And if you use not L1 norm, but L2 norm, so this is L2 norm. It's not called lasso, it's called rigid regression, but the same idea. Just use L2 regularized regression. This is still the regression, the difference between observed and estimated. So if you have this penalty term for the parameters, then this is called a rigid regression. Yeah, I want to skip this. So basically, this is a procedure to illustrate how the L1, L2 norm will help you to reach the first solution. Okay, so in this is a place where you only keep beta 2 and put the beta 1 into 0. Okay, so this is a solution you found using this penalty term. So this is lasso, use L1 norm as a penalty term for the parameters space. And this is rigid regression. And there's another called elastic net regression. This is a combination of the lasso and rigid regression. And this is a norm 1, this is norm 2. So this method adds 2 terms as a penalty for the introduction of the new feature variables into the model. Okay, we will have implementation. The lasso is a built-in function in MATLAB as well. So I want to jump to next topic. All right, so we finish regression, we finish lasso. So next time people say lasso, and you know, it's just select the most important feature variables. Okay. The procedure built into the optimization problem, and then automatically gave you the feature selection of the most important features you use. So the next topic, we will look at a single cell study. It's a bioinformatics study to solve the problem, see whether single cell expression variability has some functional meaning. You know, when we use single cell, we start to look at individual cells, gene expression, and to have a ultimate the resolution of individual cells. So the difference between this expression level compared to traditional RNA-seq or microarray is you can start to look at the variability among cells rather than as a group. Sometimes if you have dealing with a homogeneous population of cells, something like this, there's no cell type. Every cell is in the same type of cells. It looks identical. There's no difference. Okay, we'll look at them. However, if you measure the particular given gene's expression, you will see one cell will express this gene, some other cell will not, and also the magnitude of the expression may change greatly. So when we see that, traditionally biologists say, okay, this is a gene expression noise. So whether those noise tell you something about the cell state or cell function, that's our problem. So Jin-Yoon Kim is a professor in, yes, Victoria, I have a problem here.
I have a question.
Question, yeah.
Because I know that in our QC, we often remove mitochondrial genes and ribosomal genes, but mitochondrial genes can indicate cell viability, but is there any importance to the ribosomal genes?
No, we don't, normally we don't remove them. We just use this as a indicator of the quality of the cell. Yeah, we don't remove them. We still keep that in the analysis. Yeah. You can remove if you like.
Yeah, like you can remove it in the toolbox, but I was wondering if there was a benefit or like pros and cons.
For the downstream analysis, I don't think there are any problem if you decide to use less genes to study some procedures. Yeah. Yeah. So so he's a professor in the Pennsylvania, UPenn, Pennsylvania, University of Pennsylvania. So we invited him to come to give a talk, but he was too busy and he rejected the invitation. In 2015, he published this opinion paper, say variation is a function. And single cell difference functionally important. So he's talking about the same type of cells, but it's just variability, so-called gene expression noise. So at that time they didn't have enough single cell data to test because the 10x genomics appeared in 2016, at the end of 2016, and become more popular in 2017. So later we will have enough data to look at those variability. So variability, what I mean is they all the same type of cells, okay, for any given gene, for example, these genes, and the gene will not express all the same cells, but some high, some low, okay. But globally, they all the same type of cells. They all in the same state, but still you have this wobbling of the expression. You never have uniformly expressed in the same level of those. But the variability is different. Some genes may have a really high variability. Some may be wobbling, but still globally the similar across cells. So we want to compare those two different type of genes, see which gene is more important in terms of cells function. So the experiment we use is to collect published data, one from lymphoblastoid cell lines, another from lung airway epithelium cell, another from the fibroblasts, and then we use another cell type, but I will ask you what cell type this could be at the end of this introduction. Yeah, so those are the Chinese, Japanese. I use this talk in Japan once. Okay, we actually did lymphoblastoid cell line single cell RNA-seq ourselves in the lab. So this is original data. This is from a cell line that we just play with this matrix, and those are the cells, those are the columns are the genes. This is just, of course, just a small set of the genes. There's only 200, but in reality we have 8,000 genes. The first, we sort the cells by their cell cycle. Okay, this is G1, this S, the G2 phase. What you can see, S and the G2 phase cells in those genes are more yellow. Yellow means the expression level is higher. So globally, these cells in S phase and the G2 phase are larger, and their mRNA probably more than G1 phase cells. So you can see globally this change of the expression level. What we want to measure the gene expression noise. What that means is in the homogeneous population of the cells, they all cell same type. Now it's the same cell type. They all cell line cells, but we want them to be in the same state. Okay, so we get rid of those cells. Only focus on cells in G1 phase. Okay, we don't want to see the difference of gene expression is caused by cells in the G1 phase against G2. We are not interested in those. We are interested in the gene expression difference between cells, but those cells are homogeneous population of cells. So this is the first step. We only focus on the same cell type, all the cells in the G1 phase of the cell cycle. We remove mitochondrial genes because each cell have a different number of copies of mitochondria. So you measure that difference. That only probably tells you the copy number difference of the mitochondria. We don't know how to interpret those. So we remove mitochondrial genes and also keep library size. We select not too high, not too low. So library size, the total number of sequence in the cell are almost the same. Then we are going to use embedding algorithm to visualize the relationship between cells. So if you use t-SNE, UMAP, PCA, and FATE, you get a slightly different embedding. So we decided to use FATE because FATE to help you to, even you have a look homogeneous population of cell, but the FATE will still show you some cells have this trajectory structure, some of the cell group here. And then we select cells, just manually drag in the in MATLAB to select those cells within the center of this cluster. Okay, the whole purpose of this multi-steps is try to get a group of cells as homogeneous as possible. All right. So we only work on the cell we selected within this particular circle. Okay, those cells we call homogeneous cells, and then just look at their gene expression of different genes. These are two types of different genes. By the way, these genes have been ranked by their average expression. So this gene and that gene, they have a similar expression average across the cells. And this is a small ribosome protein subunit, and its expression profile looks like this. In the select cells, it's almost 1,500 cells. All the cells express that particular gene. No single cell express 0. Okay, but the level is about 150 or maybe less, 100 or okay, just like that. Well, this gene is very different. A lot of cells have no expression of that particular gene, 0. Okay, maybe more than 50% of the cells have 0 expression, but another set of cells express this gene, but the level is really high, either 400, 200, or some over 600. So this is all UMI counts. So when you take average, these two genes have a similar level average across all the cells, but their noise pattern is completely different. So we will consider this as a more noise expressed because it's unpredictable, either 400, either 0, 200, 0. Well, this is more uniformly expressed, even though there's some fluctuation across the cells, right? How to measure this? You use standard deviation divided by mean. Okay, you compute this called coefficient of variation. So for this gene, the CV is 0.43, and this gene, the CV is 6.38. As I said, they have a similar mean, so mu almost the same across all the cells here. But the variability, the variation is much higher in this immunoglobulin gene. All right. So if you plot these two genes in this scatter plot, for two genes, this one, this another, so they have a similar mean. So this is a log-log plot. And then you have a similar mean of this, but one of them have a higher CV. So this will be the hemoglobin, and this will be the ribosome protein. It's in two different places. So we plot all the genes out. You see this before, and you should expect to have a linear relationship between mean and the CV if you gene expression follow this Poisson distribution. So if you plot all the genes out, you can see there are clear negative correlation between genes average and their CV. So each point is a gene, okay? So the gene, the estimation is from this table. They are homogeneous population again. And for this, you can do a linear regression. Okay, you can fit a curve here. You can also add a nonlinear term. So you have this, either you fit with the right line or this green curve, either way. So what we want to compute is your observed CV, the variation, against your expected. So if you if this gene follow the trend of global other genes pattern, this particular CV should be here based on its average. Okay, but you observe this gene which jump out from this curve quite a lot. So how far away you jump out from the curve is an indication how noise your expression is. Because the majority of genes follow this pattern. If you have a high expression, you have lower variability. But this gene, for example, is not follow this rule at all. If it follow that rule, it should have CV at this level because the expression is so high. So we compute the difference between observed CV, so that Y value, with its expected value by this regression. The difference between this called the residual CV. We use this as an indicator how variable this gene expression is. Okay, basically if you jump away from this curve to a larger distance, then you have a more variable expression measurement. So in this place, we used this linear regression, okay, to fit the mean, to use the mean to explain CV. There's some transformation, take a log, and then after you change to log, the almost linear, but you have to deal with some of this curve at the end of this high expression genes. So this we used this so-called generalized linear models. So to allow you to have this nonlinear term there. Anyway, so this is the fitting. That's from the real data. And you see, okay, some genes jump out above this curve. Some is lower than this curve. So I put some example genes. And the 4 is above this curve, 4 to down below this curve, to look at their expression profiles. So these two are these two genes which below this curve. Their expression is homogeneous, basically. It's expressed in all the cells and in a similar level, and the magnitude is from 0 to 35 for this ribosome protein, as from 0 to 1 to 10 for this transmembrane 9B protein. But these 4 genes, which way above the curve, expressed like this. The magnitude is from 0 to 1,000. Okay, some cell express this gene 1,000 almost. This is 0 to 200. This is 0 to 1,200. This is 0 to 200. There's a lot of zeros as well, empty cells. So the genes above this curve have more variability than expectation. Those genes we see, it's called highly variable genes. Okay, again, this definition is based on all the cells are the same cell type, same states. There's no way to distinguish them computationally, basically. We try the best. They are still clustered together. So within this population, we have highly variable genes against non-highly variable genes. Then we'll start to look at, for lymphoblastoid cell line, what are those highly variable genes? We just pick those genes which way above the curve, and who is the most variable one and second most variable one. So those are the genes from the top 50 highly variable genes from lymphoblastoid cell line. Then we search the enrichment analysis using enricher to look at, as a group of those genes, what their function are associated with. So we see a lot of immune system response. The most important may be cytokine mediated signal pathways. So basically it tells you what the cell you see here is a type of immune cells. This is true because lymphoblastoid cell line is a human B cell derived cell line. So itself is a B cell basically. So this is lymph cells in the immune cells. So this example tells you the function of those highly variable genes is associated with the expected function of those cell type. So this is regression and also the curve of all the genes for epithelium cells. So again, we can find, okay, so which gene are the highly variable genes? We just pick those top 50 genes and put in this table. This gene is very different from the one from lymphoblastoid cell lines. They are different set of genes. So function of those genes, including extracellular matrix organization, response to chemicals, collagen formation. So looks like all the function you can work out from these combinations of the gene sets related to the epithelium cell in the lungs. There are some of this immune-related cytokine signaling, but probably the epithelium cell also have a play a role in there. Okay. But this term I will highlight the collagen formation. It's different. You only be able to see that in the lymphoblastoid cell lines gene set. Again, so this set of genes is not a random genes. Those are the functional related genes for the epithelium cells. Now let's jump to the fibroblast. Okay, again you see some genes jump out from the curve. And those genes, the top 50s are those ones. The one that caught my eyes was this keratinization. Okay, it's a form of this skin. Okay. So you don't see this term in lung endothelium cells. You don't expect to see you have a keratinization within the lung. That's not good. But in the skin, this is important function for those highly variable genes to play with. Okay. If you search for the top highly expressed genes, you won't get this term at all. Okay, so what are the highly expressed genes? Are those genes highly expressed? That's only consider mean than this end are those genes. Those highly variable genes encoded the function of the cell type, the function of the cells, but not those highly expressed genes at all. To summarize, so we look at the highly variable genes in 3 example cell types and identified their enriched function, including lymphoblast cell lines, cytokine signaling. For epithelium cell, lung airway, you have a collagen formation. Well, in the dermal fibroblast, you have a keratinization. Okay, you cannot make this wrong. There's no. As I said, I have another, the 4th cell type. I didn't tell you what they are. The pattern you see from the regression scatter plot is very different from the other 3. For this cell type, there's almost no gene jump out from the curve. All the genes follow this regression line nicely, cleanly. If you compare what you see previously, you always see those genes jump out. But for this one, not even a single one. So my question for you is, what this cell type is? Which cell type? This. Computationally, we just deal with this cell type data the same. So found a homogeneous population of cell, do the same exactly analysis, but this one just 0 highly variable gene at all. Myocytes? The muscle cell. We can try muscle cell. You can give it a try in your homework, see muscle cell, whether you get this pattern or not. I didn't know. Non-differentiated. You are right. Yeah, you are right. So this cell type is non-differentiated, non-function. We were very surprised when we see that, because we didn't expect it to have this. This is a induced pluripotent stem cells. So we just try this. There's no function predicted. Very good. So we summarize the difference between what we observed. This is a hypothesis, okay? Because stem cell has not differentiated into any registered function cell yet. So there's no gene has to be active or become highly variable genes. Well, the other 3 cell types, they have been fully differentiated into particular cell type already. So they have to maintain their cell type specific function. So those genes start to show this highly variable expression patterns. So if our hypothesis is true, and we should be able to test this using another data set. This data set is from epithelium cell, iPSC, okay, stem cell, and differentiate it into neuron stem cells. And then you can further derive that into astrocytes, oligodendrocytes, neurons, etc. But this neuron stem cell is intermediate step. So it's in between of the half differentiated, half non-differentiated. So we expect if you plot out this kind of curve, scatter plot for this cell type, this should have a pattern which in the middle of the non-differentiated and differentiated. So if you look at these figures from neural stem cells, it's indeed we found there are some genes start to jump out from the curve. Some of this, if you look at closely, but not yet to the extent of so the magnitude of this, the trend is not as clear as your fully differentiated cells. So what we believe, this curve can tell you whether the cells you studied, the population, whether they're differentiated or not, or what type of gene differentiated and registered for what kind of function by looking at those jumped out genes. We tried this in, for example, clouding sites. This is very special epithelium cells, endothelium cells probably, epithelium cell in the bile duct. And with what we can find the function of the enrichment, including response to corticosteroids and the different kind of the hormones. Okay, so those epithelium cells in the duct surface and the function of those is really specific, highly specific to response to the hormone internal stimulus. So this is not random. We strongly believe if you, for example, you don't know what this cell type is working on, what their main function, most significant function, by just looking at their highly variable genes, rather than to look at which gene expressed high in these cells. Those are the useless information. Look at the highly variable ones, okay, by checking the noise of those genes. And yeah, so those are the review paper to talk about the epithelium cell in bile duct and the physiological of the collagen sites. Okay, that's including the stimulate the secretion of steroids. So it starts to make sense to us. Okay, so I hope this small study tells you don't only consider expression level high or low when you study single cell. I say don't rely on the DE, differential expression. Differential expression is to compare one condition against another, say which gene upregulated, higher or lower. Consider the variability, okay? The single cell expression variability exists in all the genes. All the genes you found this variability, this noise. It's just some of these have higher, some have lower variability. The level is different. In different cell type, you will find different sites of the highly variable genes. Okay, and then you look at those highly variable genes by checking their enriched function group as a gene set. You probably can get some good idea about what the cell's function is. Okay, so that's all. We will play with some data, real data. You can select, for example, you can select muscle cells, see what in the muscle cells, what the highly variable genes are. See whether it makes sense or not. Yeah, we will try this Thursday. All right. Okay, see you on Thursday. Okay. you.